the audios. Yep. Okay. So let me get started. So just to kind of recap where we are, we're in chapter 2, right, which is mostly on graphing and functions. And so far we've defined like what a function is, how to find its domain, how to find its range. I've talked about last time about like how we can decide whether or not a given graph or equation represents a function, right? So we looked at that. And so essentially we're up to section 2.6, give or take, all right? I don't really have much to say about linear functions and models, which is I think section 2.4. I'll let you look at the homework there. There's really not too much to say there. What's a linear function? I mean, I guess I can say this much. If you have f of x equals to mx plus b for some m and b constant, then this is a so-called linear model. I mean, well, linear function, I suppose. Now, technically speaking, this is at odds with a later use of linear that we do in math. Like later in mathematics, when we talk about a linear transformation or a linear map, it's assumed that that constant b is 0. So if you end up being a math major, that will be important to you. And we'd call in a function like this what's called, it'd be called an affine function, which just means like linear plus a constant. That's pretty much all I have to say about it. That section in your textbook, it gives you some examples, like examples of linear functions abound in nature and so forth. So that's about all I have to say about that. But what I have much more to say about today, if I can find my eraser, aha, here's my eraser, is transformations of graphs, all right, which is section 2.6. And so I guess first thing I need to do, let me tell you our goal. Our goal is to learn how to quickly and easily identify standard graphs via transformation rules. Okay, this is essentially section 2.6 in your textbook. And so let me just kind of give you the big picture. The big picture is we have this like standard list of examples. All right, there's about 10 basic functions that we know the graphs of. And once we know these, we can take them and we can move them around, we can flip them over, we can stretch them out or compress them to form new graphs. All right, so the first thing we got to do is to make sure we know like our standard list of examples. So let me just go through them, right? And some of these we've already done, like y equals mx plus b. You know what that is. What's that look like? It's a line, right? The slope is m. Y-intercept is b, right? So that's what that looks like. I guess next I would add to that y equals the absolute value of x. What's that look like? It's y equals x over here. It's y equals minus x over there, right? And those two join together at the origin to give you that corner, right? Which is, by the way, an example of a local minimum. See that? Local minimum. So 3, you have y equals x to the 2n, where n is 1, 2, 3, and so forth, right? So that would be like y equals x squared y equals x to the fourth, and so on. Like as you go on out and get higher and higher powers, remember we talked about it looks like a goalpost if you look at like x to the 100, right? We know that. 4, you could look at y equals x to an odd power. How do we write an odd power? We could write it as 2n, 2n minus 1. Well, I guess I'll write n plus 1. That way it'll start at 3, right? So, for example, y equals x cubed, or y equals x to the 5th, right? So we look like this. X to the 5th kind of looks the same, but it's more steep. What other kind of standard examples do we have? Did I already go through this list in here? No. I think we just looked at it on the Desmos, right? A little bit. You can also talk about y equals like the 2nth root of x. So like an even root. Even root functions, the way I understand those is to think about doing the algebra. So like if you solve for x, how do you solve for x here? How would we solve for x in this equation? Square both sides. How about we, I mean, I like the idea, but I take your square and raise you a 2nth power, right? Because like this is the 2nth power. So, but that's the right idea. So we get y to the 2n equals to x. So basically, this is just like that or that, except that we've we've interchanged the roles of x and y. So what I'm trying to say is we can look at the square root function as like, I mean, here's y equals square root of x. Actually, this one down here is what? Minus the square root of x. So we don't get both because the definition of even power is we take the positive root, right? If I take like 16, I say, what's the square root of 16? The standard answer is 4, right? But technically minus 4 is also an example of a number which squares to 16, right? Minus 4 squared is 16. But it's our convention to use the positive root. And we say that that's the square root. Okay? So by definition, the even roots are positive, which means we're kind of like erasing this part of that graph. But if you just want to visualize what does an even root graph look like, it's like half of a parabola. Or if you were to look at the fourth root, it'd be like half of one of these guys, right? So if I was so foolish as to try to graph the fourth root, it would be more like this. And I'm not quite doing it justice. They both go through 1, 1. Just like it's something like that, the orange. The fourth root is below the square root when you're less than 1. But once you get beyond 1, it grows faster than the x to the fourth is smaller than x squared if you're less than 1, but it's larger than x squared if you're greater than 1. So they cross at 1, 1 or minus 1, 1. Like these guys, they all have the points 1, 1 and minus 1, 1 in their graphs. They like all intersect through these points. And so likewise, when you look at these guys, the point 1, 1 is like in the graph, and so like square root's more like this. But the fourth root, if I was to draw it, would be more like that. I'm going into entirely too much detail here because this really is not the spirit of the graphing we'll be doing after about 5 minutes from now, okay? But the what? Oh, even root function. That's my horribly mangled function. So rather than writing out function, I'll write FNCT. That's like an abbreviation for function. So, because I get tired of writing Fucntion. So those are even root functions. Basically, this isn't even here because we don't count the minus root in this discussion. By definition, this even root is the positive root. Well, technically the non-negative root. Any even root of 0 is 0. So we could have 0. 6, you can have y equals to a odd root. I'm trying to make myself room to write 2n plus 1, like an odd root. So for example, this is y equals the cube root of x, something like that. I think there's a question. What's the question?
What are your exponents for number 4 where it says y equals x?
2n plus 1.
Okay, no, down below that.
This one?
No, go back up. Above your graph on number 4. Above your graph on number 4.
Above my graph.
Yes, okay, that's a 5. Now go over.
Oh, I gotcha. This is a 3.
Okay.
Sorry. Is there like a glare on the board there or something? Or it's just too small?
No, I just couldn't read it.
I gotta ask the dean if I can get some binoculars for the back row, something like that. Maybe we could like make one of those like sightseeing things, like bolted into the desk. You can put it up there. Yeah, and then before class I could go in and like paint it with ink. It'd be hilarious. I could put that on my math pranks. Although technically it wouldn't be a math prank, so it wouldn't really be true to the spirit of the channel. I think I'm digressing. So can you guys think of any other standard examples that we might want to move around? How about the reciprocal function? And here I'm just going to keep it boring. I'm just going to say y equals 1 over x. That looks like this, right? Basically, that's what y equals 1 over x looks like. And I've run out of room. I guess I'll put it up here. How about y equals 1 over x squared? This is the volcano function. It goes to infinity like that. So if you know these, and I feel like I'm missing a couple. I don't know what I'm missing at the moment. I'm missing something. I mean, you guys know what the constant function looks like, right? Just horizontal line, right? There's that one. But if you know these, it's a pretty good starting point, right? My point to you is if you're asked to graph any of these formulas, you really shouldn't need a graphing calculator. You ought to be able to just say x, x, y, and just kind of freehand it and go, it's roughly like this. That's what I'm trying to get across, right? Because it takes time to get out a graphing calculator and when I give a test in here, it's not always just about the test, right? But just to talk about the test for a second, I never intend for you to need a graphing calculator on my test, right? So, okay, so these are our standard graphs. And now we can start talking about transformations on graphs. So let's talk about it. And so here's the transformations. So what I'm going to do, so this is new graphs. New graphs from old, you could say. So here's our starting point. Given y equals to f of x, for f being some function, number one, y equals to g of x plus c, and we're going to suppose that c is positive, all right? At least for the initial discussion, I'm going to assume that c is a positive constant, all right? Once I get through this list, I'll start talking about what it means if c is negative. But if c is positive constant, if I look at y equals g of x plus c, what's that graph? How does it relate? This is a shift up, right? We shift up by c. That's what that does. 2, if we look at y equals g of x minus c, this is shift right. That, I know that's counterintuitive. You might want to think it's left, but it's not. It's right. I will give you an example. Let's actually look at the example before I go further. You want to leave yourself room in your notes. I'm going to write about 6 things here. So if you're making a list, leave some room. And I'm going to put the examples over here.
Real quick,
Go for it.
does that say new graphs
From old? Yeah, new graphs from old. All right, so example. First of all, I'll do the easy one. If we take y equals x squared, right? That's this, right? And then if we do y equals, I'll do it this way, up 1, right? So if we add 1, we just shift up 1. That's how that works. Example 2, what happens if we take the same y equals x squared, which looks like this, right? And we go right 2. That would be over here, right? So if somebody gave you a parabola that bounces off the x-axis like that, what's the formula for it? It's got a repeated root of 2. What's the formula? Y equals what? X minus 2 quantity squared, right? We haven't talked about graphing in here, but we have talked about completely factoring, right? So when you think about a quadratic polynomial, when you completely factor it, it's like a square repeated. What that means is that the graph bounces off the x-axis, right? Just that one point is where it hits the x-axis. It's got one x-intercept. In this case, it happens to be 2. So I know it's a little bit counterintuitive, but when we subtract a number from the argument of a function, it shifts the graph right. The reason that it's different, 1 and 2 are different, is that they're very different, right? I mean, number 1, we're adjusting the dependent variable y, right? Whereas number 2, we're adjusting the input, right? The independent variable x. So there's a difference between the output and the input of a function. That's why these are different. But there it is. I mean, this isn't part of my list, but I would just make a remark at this point. Think about this. If we think about the standard circle, x squared plus y squared equals to r squared, right? That's centered at the origin, right? Versus what? X minus h squared plus y minus k squared equals to r squared. See, if we shift both of these like that, what does it do? It moves the circle where? From the origin to the center h comma k. So, it seems so happy. Sorry. At some point, these chalk suicide jokes are going to get me into trouble. Probably shouldn't have explained the joke. Let's see here, h comma k is the center, right? So my point to you is, if you look at an equation where x and y are treated equally, then the transformation rule is symmetric. We subtract h, we subtract k, that moves us h over and k up. The reason for the distinction in 1 and 2 is because we're looking at a graph versus the input to the function, you know? Anyway, enough about that. I'm going to give you a second to copy. I'm going to erase this remark before too long. So what's next on my list here? 3, I guess before I get too much further, let me talk about y equals 2. Oh, come on. What I was trying to write here, guys, graph y equals g of x is 1 for g of x equals to f of x plus c up by c. Sorry, I'm having trouble with my grammar today here. For g of x equal to f of x minus c, right. You don't have to erase your notes, by the way. I mean, I think you can see what I was saying. I mean, the g of x is defined in terms of the f of x. I'm saying g of x is the new function that we're modifying the old function, all right? And I had written my modifications in terms of g again. It was like, it didn't make any sense. You know, I meant to put f of x here and f of x there. My apologies. 3, we could look at g of x equals to minus f of x. This is what? And we could look at g of x equals to f of minus x. What do you say this one, what was 3? It was do what? Say it does it flips what? Flip over what? Can I erase this now? Okay. Okay. Every so often, I've got a student who is 5 minutes behind me in lecture, so I got to be careful. So if we go from y equals x squared, right, looks like this. And if we look at y equals minus x squared, what's that look like? Let me draw it on the same axis, actually. It's what? Upside down, right? Is that right? Thank you. I can't count, you know. So yeah, y equals minus x squared. It's upside down. You could also say you flip over the what? X-axis, right. So what do you think the next one is? Right, flip over y-axis. Now, what happens when we look at y equals minus x squared here? What is minus x squared squared? I mean, this, rather, upwards. This is minus 1 times x, right? Which is minus 1 squared, x squared, right? Which you guys know is x squared again, right? I mean, I'm having trouble drawing the exponents at the top of the board right now. Sorry about that. So if I was to graph g of x as f of minus x on my current example 3, what does it look like? It's already there, right? What is that what does that tell you about this function, f of x equals x squared? What did we say this kind of function is? It's called a even function, right? So an even function geometrically is one that when you flip it over the y-axis, the graph doesn't change. Same graph. We also say it has symmetry with respect to like a flip over the y-axis. So we're not be able, we won't gain much intuition for number 4 from this example 3, right? We should look at something else, like how about the absolute value function? So I'll do absolute value of x. I'm going to make it a little bit more interesting. Absolute value, y equals absolute value of x plus 1. See that? So if I know the absolute value function, then I know that if I add 1, it just shifts it up 1. Right? So it looks like that. What if we, so I'm thinking of that as my f of x. What's f of minus x? Oh, man, I just did it again. What can you tell me about this? What's f of minus x? What's the absolute value of minus x? Say again? Flip over y. No, my question though is what is the absolute value of minus x? X. It's the absolute value of x again. What does that mean about my next example? It's again an even function. So this is a very poor choice on my part, is it not? To illustrate number 4, isn't it? Because again, if you flip this over the y-axis, we're right back where we started again. It's even, isn't it? All right, let's see if maybe example 5 will go better. Let's try. See if I can finally find my way to a function which is not even. How about this? What if we do y equals absolute value of x plus 3? What would that look like? We take y equals value of x and shift what? Yeah, shift left by 3 units. So I guess now is as good a time as any to tell you how does 1 and 2 modify if we let c be negative? The opposite, right? If c is negative, we shift down. And if c is negative here, we shift left. But of course, minus a minus is a plus, right? So like x plus 3 is x minus minus 3. We shift left 3. And of course, that looks like what? So there you go. This is y equals absolute value of x plus 3. So if that's my f of x, what's f of minus x? What? I'm going to make the so f of minus x would be absolute value of 3 minus x, right? I think a nicer way to write that, though, is that this is the absolute value of x minus 3. Like, it's easier for me to see what's going on if I write it that way. So you're right, it's the absolute value function shifted 3 to the right instead. So here's y equals to f of minus x, when that's f of x. So of course, is this function even? It is not, right? When we reflect across the y-axis, we get a new graph, right? So anyway, that's an example of what a non-trivial flip over the y-axis would look like. It could be something like that. Another example, we could look at f of x equals the cube root of x, then g of x equal the cube root of minus x. What's that look like? What happens when you take the cube root of minus something? So this is actually, by algebra, minus the cube root of x. So let's see here. If the cube root looks like this, then minus the cube root looks like that. So you can see this actually as an example of two transformation rules at once, right? On the one hand, it's an example of number 3. We're flipping the graph, what? Over the x-axis, right? It's like you flip the white chalk over the x-axis, you get the red, you get the orange, right? But also, if you flip the graph over the y-axis, this is a kind of funny function. It actually, you could look at it either in terms of transformation 3 or transformation 4. They both do the same thing. But incidentally, this is an example of an odd function, isn't it? Because we have f of minus x equals to minus f of x, right? In this example. Okay, moving along. 5, if we have g of x equals to c times f of x, or 6, if we have g of x equals to f of cx. These are, maybe, so in some sense, you can kind of think about 3 and 4 as special cases of this, but I am assuming c is positive, so I guess not. But for c positive, what this does is it stretches the graph out vertically, right? And this compresses horizontally. The stretch vertically is pretty easy to understand. Show you an example. Before I do that, though, is there any more questions about my unnumbered example at the bottom of the board? What is that, example 6? 7? Somebody here is counting. 6, okay. Any questions about example 6? Okay. So example 7, we could do something like y equals x plus 2. Let's say x plus 1. Right? Versus y equals to 2 times x plus 1, which is what? 2x plus 2, right? So if I was to graph that on the same graph, what would it look like? What happens for both of these at -1? It's 0, right? It was supposed to be a line. Use your imagination. Think of that as a line. Or let me try this again. Well, anyway, I tried. I guess that's something that might be useful. If, think about this. If f of x naught, if you had f of x naught equal to 0, then c times f of x naught equals to 0. What that tells me is that if I take a graph and I stretch it vertically, right, any x-intercept of the original graph will still be an x-intercept of the new graph. It's going to move the y-intercepts around, right, because you're like stretching it in the y direction, but the x direction, like the zeros of the original graph, will be shared by the new graph. That's kind of a helpful principle as you're thinking about creating new graphs by stretching. The zeros on the x-axis stay put. You're just stretching things away from the x-axis by a factor of c. Is good? Now, this compresses horizontally. It's always a little bit counterintuitive to students, and I think a good, if we look at a good explicit example, maybe I can convince you that that's how it works. So let's look at something that has a nice horizontal feature, something like x equals to x squared minus 4 is good. X squared minus 4, we should talk about how do we graph something like that? What do you do? Well, if you follow the instructions from today, you take the y equals x squared graph and you do what? Shift down by 4. Oh man, poor planning on my part. The interesting stuff is mostly happening below the y-axis here. So this is minus 2, and this is 2, right? Which we can understand from completely factoring this to x plus 2 times x minus 2, right? So it's not like a either or. I mean, we can use the things we know in concert, right? Transformations of graphs, that knowledge we can marry with what we already know about completely factoring polynomials, right? When we completely factor a polynomial, that shows us where the x-intercepts are, if there are any, right? In this case, there's x-intercepts at plus and minus 2. So we actually get 3 kind of easy things, that this is at minus 4, and that these are at 2 and minus 2, right? Okay, so I'm thinking of f of x equal to x squared minus 4. What would it look like if we looked at f of, let's say, 3x? What would f of 3x look like? Let's do the math. 3x squared minus 4, right? That's the rule. We square the input and we subtract 4. So this is part of the reason I was talking about evaluation the other day, right? It's something we have to do oftentimes as we consider problems in pre-calculus. We end up evaluating functions at something other than x. It's a skill we have to acquire if we don't have it already. What is 3x squared? I mean, so we could square this out, or we could just kind of like think about this as the difference of squares and like factor it immediately. What do you guys want to do? Let's factor it immediately. What's 4? It's 2 squared, right? So we could immediately factor this as 3x minus 2 times 3x plus 2. That would be the lazy thing to do here. And so that's the right thing to do. So where are the zeros of g, of this new function? Let me call this g of x, because that's what I've been calling it. What are the zeros of this transformed function g of x? We need what? We need 3x minus 2 equal to 0, or 3x plus 2 equals to 0, right? So either x is equal to 2/3 or minus 2/3, yeah. So the transformed functions has zeros not at plus and minus 2, but plus or minus 2/3, right? Which is like here somewhere. And where's the y-intercept of the transformed function? Notice that there's a symmetry here in the logic. The y-intercept is not changed for step 6, right? F of 0 is equal to f of c times 0. And if you think about that, if f of 0 is equal to f of c times 0, that means whatever is a y-intercept for your original function is still a y-intercept for your transformed function. And we're seeing that in our example. Like minus 4 is still the y-intercept for the compressed function. It's just that it's squished by a factor of 3. Okay. So once we have all these, let's say, cards on the table, then we can combine these things and look at functions that are built from some sort of, a few of these transformations combined. So let's see if we can do some of these. Again, we're in section 2.6. And I'm sorry I have not written your mission 3 yet. It's bothering me.
Oh, it's okay.
All right. So the problem here is to explain how g of x arises from f of x transformed. So let's see here. Number 46. We're going to have y equals to the square root of x plus 4 minus 3. So let me tell you how we can think about this. What we start with y equals the square root of x, right? Then we're going to go left 4, right? Left 4 goes to that. And then we go what? Well, let's say we go down 3. So if I make a picture, we're like starting with y equals square root of x, right? And then we're doing what? We're going left 4. And then we're doing what? Going down 3. So it looked, I mean, I'm not quite right. It would cross the x-axis eventually. I'm not sure exactly where, but something like that. So we can graph something that is related to one of our standard examples, in this case, the square root function, by simply shifting around as just like that, right? Now, you're like, well, that's not how I looked at it. I thought that you should shift down first, right? And then you should do what? You should shift, go left. Left 4, right? And guess what? Same thing. That is not to say that the order of the transformations is universally like, I mean, sometimes it matters which one you do first and which one you do second. Particularly if it involves the flips over the x or y axis, those don't usually, they have to be done in a certain order, and if you reverse the order, it changes the way it happens. Another example would be number 52. This is from section 2.6. We have y equals to 3 minus twice x minus 1 squared. So here's what I would do. I would start with y equals x squared, right? Then I go to y equals to x minus 1 squared. Then I flip it, or I could multiply by 2. Then I multiply by minus 1. And then finally I add 3. Tracking through the pictures, it would look like this. So squared, then we move 1 to the right, then we multiply by 2, then we flip it, and then we add 3. So roughly speaking, the parabola looks something like that. I'm being very fast and a little bit careless because I only have so much class time. But if you had graph paper and this was, homework or a test question, you could have time to like carefully go through these steps one at a time, right? So a problem I might have is like, find 3 transformations and draw the original graph. Starting with this graph, I would fix the original graph for you probably, and then say, give me a transformation followed by another transformation followed by another transformation, which gets you to the end point. And you could graph each step in between like this. Anyway, I would just encourage you to pay special attention to the recommended homework where there's pictures. These are like super helpful. Finally, let me just tell you something about next week. Next Friday, I will not be here. I'm selling my house, so I will be in a different state. And I won't be here Thursday either. So what do you guys think we should do? Oh, you want to turn off the camera? What's that?
We'll see you then next Monday.
You'll see me the Monday after. Okay. I mean, so what I'm thinking I should do is record a video for you, and then you can watch it at your leisure sometime between Wednesday and Monday. Sound good? I think we should be through all the new material by Wednesday, though.